Continuing on with the discussion of internals of Java, we're going to talk Java streams. We're going to talk about how a Java stream is constructed. And this is actually quite interesting and tells you a lot about what's happening under the hood. So if you recall our earlier discussions, I kept mentioning that a Java stream is lazy, which meant that the intermediate operations don't do anything until the terminal operation is reached. So nothing starts to run until a terminal operation is reached. And now I'm going to kind of show you exactly how that works. So let's take a look at a simple example to illustrate this. This example is going to take a list of strings, turn it into a stream of strings, uppercase all the strings, only allow strings that start with the capital letter A to continue. Then we're going to sort everything that starts with the capital letter A, and then we're going to collect the results into a list. So that's going to be called sorted A words. So that's what we're going to do. And what happens when your program runs, so remember your Java compiler will compile this code into some executable format like bytecode, or if you're using a just-in-time compiler like implementation, or you could actually compile it into binary code if you're using an ahead-of-time compiler. But whatever you do, the compiler compiles this into code. And what this code does is as it runs at runtime, instead of actually executing those operations, it builds up at runtime a linked list of the stream source, which in this case is this list of strings, and all the intermediate operations. And in this linked list, every node in the linked list corresponds to a stage in the pipeline. So these are kind of the stages, right? This is sort of the linked list that's being built. So the linked list will contain the input, which is the list. Then we'll have the map method. Then we'll have the filter method. Then we'll have the sorted method, or maybe I should use the word operation is probably a better term. So we have the map operation, the filter operation, the sorted operation. Those things will be put into a linked list. And then when the collect operation is reached in the linked list that's built up, that's when the data gets pulled through from the source through the various stages in that pipeline, and those operations and their behaviors are then applied on the data that flows through that stream. So that's why nothing runs until the terminal operation is reached, because until that point, the runtime system is building that linked list as it's seeing what was compiled into the code. And then when collect is hit, in this case, then things start to run. Now, as that linked list is being built up, each stage in this pipeline is described internally by a bitmap of flags. They're called stream flags. And these flags will describe each of the operations that exists in the stream. So for example, one of the flags is going to be sized, and that says the size of the stream is unknown. So there's some streams that have unknown size. A good example would be a stream where you have an array list and you say, list.stream. We know how big it is because it's whatever the size of the list is, right? Other situations, like if you think back to the iterate factor method that we had on stream, we don't know the size of that stream. That stream is unsized. So there's certain methods that will yield unsized streams, certain methods that will yield sized streams. Another characteristic of a stream is whether the elements are distinct or not. If you have a list of something, we don't know if the elements are distinct, so we're going to assume they're not. They might be, but we don't know. And without examining them all, we can't know for sure. So we're going to assume that they're not distinct. However, if the source of the stream is a set, we know they're distinct. So there's no sense in worrying about whether they're distinct. And you'll see why that distinction is important in a second. Sorted. Are the elements of the stream sorted in natural order? Well, again, if we have a list, we don't know if they're sorted, so we're going to assume they're not sorted. But if the source of the stream is let's see what would be a good example, a tree set, then we know that it's going to be sorted. Hash set, not so much, but a tree set, it'll be sorted. And then finally, ordered. Does the stream have a meaningful encounter order? And that basically says if you go through the stream in an iterator-like manner from beginning to end, will the order mean something? And again, some sources have meaningful encounter order, like a list does. Other types of sources, like a set or a map, won't have a meaningful order. Not sorted, but the order doesn't really matter because we don't really care. You just care that they're unique. So these are examples of things that are applied to characterize as metadata the different properties of the operations at every stage along the way. And you could actually have certain things that are set. So here's a good example. An array list is sized and ordered, not sorted necessarily, but ordered, because there's like the 0th location, the 1st location, the 2nd location, the 3rd location, and so on, but not sorted or distinct. A hash set is sized and distinct, but it's not necessarily sorted and it's not ordered. A tree set is sized, distinct, sorted, and ordered. So that's an example of something that would be all of those properties. And that information is then going to be used in ways we'll talk about in order to do optimizations of the stream. Keep in mind that the generate and iterate methods that create streams are not sized. As we talked about before, iterate could go on forever, so we don't know the size. Generate's the same thing. Generate could generate forever. Now, typically in practice, we limit the amount of elements that are created by unsized factor methods like iterate and generate by using various short circuit operations like limit, for example. But at least from the point of view of the source of the data, they're not known to be sized. Each intermediate operation in the stream can then affect the flags that have been propagated from the top, from the source. So for example, if a map operation occurs in the stream, that will clear the sorted and distinct flags, but it keeps the sized flag. And that's because map takes a mapper function that could change the values and the types for that matter, but certainly the values could be changed. So something that was sorted could be no longer sorted. Something that was distinct might no longer be distinct. You might have a map method that takes every odd number and replaces it with 0. I mean, kind of weird, but that would be an example of map taking something that was distinct and making it non-distinct. But map won't ever add any more items because remember, map's input and output element count must be identical. Filter clears sized because we knew the size before, but when filter runs, it may get rid of some of the elements, and we don't really know how many until we run them. So sized is no longer going to be set, but sorted and distinct will remain because filter can't change the results of anything. So it will still be sorted. If it was sorted before, it's still sorted. If it was distinct before, it'll still be distinct. We may just not have as many elements this time. And then sorted keeps sized and distinct. We're not adding more elements when we sort. We're not changing the values when we sort, hopefully, unless you have a bug. But we're adding sorted because now the contents are sorted. So as the stream is being put together, it'll create these flags, and those flags will then be used at runtime. And so the flags of a previous stage are combined with the behavior of the current stage in order to derive a new set of flags for that stage. All right, you're probably asking at this point, why are we going to all this trouble? What's the point of doing all this? Well, here's a simple example to illustrate why we're going to all this trouble. Based on the stream's framework knowledge of the semantics of the data source and the operations that appear in the stream, it can do optimizations of things. Much like a query optimizer in an SQL query engine can optimize things, so too here can we optimize stuff. So as you can see here, this is a simple example. We make a local variable called TS, which is a new tree set. That sets the flag sorted, so we know it's sorted. We then go and turn that into a stream. We filter out things that aren't starting with capital A. It's still sorted. And then we run the sorted operation. Well, the streams framework will say, thank you very much, but I can just ignore your request to sort this because I already know this thing has to be sorted. So there's no point in even running that operation. So it's able to eliminate that operation entirely. So that's just a simple example of how the streams framework knows the semantics of the source and the operations in a stream can help it do a better job of optimizing the behavior of the stream under the hood. So that's the end of the discussion of constructing a stream.